The aim of this project is to design a simple wing structure by following the engineering design process, which consists of 4 stages: conceptual design, preliminary design, detailed design, and finally evaluation and acceptance. Before beginning the first stage, we created this timeline for group to follow.
In the conceptual design phase, we first reviewed the requirements that was given to us in the briefing document. The requirements include the dimensions and the loading specifications of the wing. As a team, we then drew sketches of the main components of the wing, which included the spar, the leading edge, trailing edge, and the rib. Following from that, we did some research on different spar designs and sketched out different designs for us to build and test during our lab sessions.
All calculations in the Excel spreadsheet take the specific design inputs as well as the material properties of foam board used in the wing's construction into account. The Excel spreadsheet is a very useful tool in early and in later stages, as it gives us specific design requirements as well as specific values for certain parameters or limits that need to be respected. By playing around with the dimensions of the spar with the interactive tool, we were able to find specific dimensions that pass all conditions/requirements. Finally, we changed the location of the spar and the ribs of the wing in order for it to fit, whilst keeping the location of the spar at quarter chord.
We tested our spar on SolidWorks for allowable stress. The objective of this was to reduce the mass of the spar as minimum as possible and to follow the design constraints of the project. We did this by identifying the corresponding location and magnitude of the stresses and the use of second moment of area equations for our desired cross-section.
We tried several different spar designs, but found that using a hollow rectangular beam with additional foam board stuck on 2 opposite sides was the most effective. Cross-shaped beam was found to be too strong as the spar didn't bend or break under stress. We then tried an I-shape, however the beam was still too strong. Ultimately, the reinforced hollow rectangular beam was the one to fit the specification and be used in our final design. We considered how we could reduce the overall weight, for example by cutting holes in the ribs, but decided that the little weight we'd save wasn't worth the time and resources it would take to complete.
The final stage is evaluation and acceptance. This is where we analyze the design by creating graphs of tip deflection and bending moment. Using this analysis, we were able to make the last changes in our design and to come up with the final product.
According to our Excel spreadsheet, for a beam of 40 by 50 mm with the extra thickness on 2 of the sides, these requirements were fulfilled. In-person testing then confirmed that the rectangular beams fitted these specifications. The maximum torsional compliance had to be less than 3 degrees per Newton meter, and the maximum deflection had to be less than 15 mm.
Finally, it is important to realize that there are some limitations to our design. Computer simulations can never replace real-life experiment, as there are some factors unaccounted for in computerized testing. We also made some assumptions for the simplicity of the design.